Hi folks, my name is Mickey Rowell. I work here at Technodyne. I want to welcome you to another series in our installation of video tutorials. The one I want to work on today is a characteristic that we refer to as roughness or smoothness. And I'd like to first start out with a little bit of a definition of that particular property, talk to you a little bit about what it is we're measuring, why we're measuring it, how we're measuring it, and a little bit about the history. We're going to be covering this particular group of series in a number of separate videos. We'll be looking at the Beck test, the Benson test, the Gurley SPS test, the Sheffield test, and the print surf test. So we'll cover those a little bit more in detail in separate videos. We'll dive a little bit deeper into the specifics of those particular tests. But what I want to do right now is to give you kind of an overview of what it is that this roughness, smoothness test is all about, maybe a little bit about where it came from. All right? So we'll go ahead and get started with the definition. All right? I say we, I'm going to make reference to the pulp and paper industry most of the time throughout this video because that's where I come from. But if we're looking at a measurement system that is providing us some results, and we're going to be looking at the roughness or smoothness property. So if we have a scale, our scale is increasing as the surface of our product that we're measuring becomes rougher. That particular definition we're going to use as roughness, okay? So an increase in the measurement scale, rougher the sample, that's the roughness measurement. Okay? We have another group of instrumentation that as the surface of the particular product that we're measuring, as that surface becomes smoother, the scale increases, all right? That particular definition we're going to offer to a smoothness test. All right, so we basically have two groups of instrumentation that fall under these two categories. Under the roughness category, we've got Benson, we've got Sheffield, and we have print surf, okay? Okay, under the category of smoothness instrumentation, we have the Gurley SPS tester. And we have the Beck test. So again, we basically have two categories of roughness, smoothness instrumentation. Probably what's going to happen is throughout this video and the preceding videos, I'm going to reference the term or use the term roughness most of the time. That's just something that I've used throughout my career, and it's easy to come by. If I make a mistake and don't technically use the appropriate definition, please forgive me. All right? So with that, I want to go ahead and talk to you a little bit about, okay, what is this particular characteristic that we are measuring? We look at a particular product. You have a printout, you have a brochure, you have some signage. Okay, what we're looking at is to quantify, and this goes back to a lot of years ago, this particular test had a very good correlation, I guess, with printability. So when we're looking at this, we want to be able to quantify what the surface of the product that we're testing really looks like. One of the ways that we've got here, use another color. So if we have a surface, we've got some bond paper, print paper, we've got some coated sheets. In every one of those cases, on a magnified level or a microscopic level, the surface is not perfectly flat like a piece of glass, but we have all these undulations in there, okay? That's the bottom surface, sorry, the top surface, and then we have the bottom surface, and we have all these little peaks and valleys throughout this whole sheet, okay? MDCD. So we've got these peaks and valleys. Now what we need to do is to quantify, are these peaks and valleys uniform? Are they extreme? Okay, do we have some very high spots, very low spots? And the purpose behind that is, again, as I mentioned a minute ago, that this particular test has a very good correlation, very good relationship with printability. So the smoother this sheet is, the less ink we have to apply, and the better defined that image becomes, all right? Especially we have a big surface area like so. We run down through the print press. We first lay on this yellow ink. And if we have some undulations that we haven't identified, we'll have missed dots all over this place, all right? Or maybe it's just in one location of that document. We want to try to avoid that. Okay, so we'll go ahead and we'll make the product, it comes off the paper machine, we run it through a gamut of tests, and we determine, okay, this is going to meet the specifications for the next process, which in most cases, like I said, are the print press printing applications. Now, certainly that's the one that's the most obvious. Another application for identifying what the surface characteristic is when we start looking at printers, whether it's a printer at home, printer at work. We want to print out a document, something like this, all right? We type it up in our word processing program. We hit the enter key to print. We want each one of those pages that we created in our digital fashion to come out a single page at a time, all right? So when we insert a ream of paper into the whether it's a copy machine, whether it's a printer, and we hit that return key, hit that print key, we expect that one sheet is going to come out at a time, be fed through the print process, and come out looking something like this. All right? If that's the surfaces of these sheets that we put in here, the ream of paper that we put in here, does not reach a particular smoothness or roughness value, we have an opportunity for these two sheets, in some cases, to actually pull out and have multiple sheets come out at a time. I'm sure maybe once in a while you've seen that, where your printer has ejected that document, but it comes out with 2 pages. Some of the document is printed here, some of it's printed here, and so forth. So we all have seen that. The reason behind that is the friction between these two sheets is too high to pull one single sheet through the printer at a time. So that's another really a key reason behind identifying what the surface characteristic is all about. All right? So if you think about these undulations, obviously we want these undulations to be maybe as uniform, but also as small as possible when the application is appropriate. So if I want a high gloss particular document like this, that surface I'm probably going to coat, but that surface really has to be a lot smoother, in a sense, than the print paper that I'm going to use in my printer or the copy paper I'm going to use in my copy machine. All right? So it does turn out, again, like I said, it's a very good predictor of printability, a very good predictor of, let's say, surface friction for transporting of the paper. All right, so I took a moment off camera, put a quick diagram together for you of an air leak measurement system This particular device was something that was used in automotive industry, manufacturing industry, machining industry, or what have you. But it was a quick method that they could use to assess whether or not their machine parts are going to fit in their assembly line a little bit farther down. What they could easily do was they have a cylinder, they've got air flowing through the cylinder pretty freely. They have a measurement device, a flow meter measurement device, so they can identify what kind of airflow is going through my open-ended cylinder. If they insert one of these dowels, that's a machine part, into that cylinder, they're going to restrict the flow. So that flow is going to, from reference to a open flow, that flow is going to be reduced. Okay, I'm going to restrict the airflow. I'm going to restrict the airflow enough so that I can take a series of dowels, bring them to my assembly process, identify which ones work, which ones don't work, and then I can quickly come up with tolerances that I can use for my process and quickly get information to my production people and be able to move that process along. Okay, so now the paper industry comes along and they read these published documentations and they look at, got this surface, top surface and bottom surface of our product. How are we ever going to be able to create a scenario where we can create some type of a pressure drop that would give us some indication of what the surface of this product looks like? And then our friends, our engineers came up with an idea that they could capture an air pocket, if you will, okay? If they had a way, they're going to have they're going to be able to have a system where we create, and the design of this system, they worked out this special design. They decided that an annular design was going to be optimum for, let's say, strength, for stability, all those types of things. And it made it a lot easier to actually create an annular ring rather than some type of a square device. So now what we've done is we have these two lands. Okay, we have two lands that are going to come down and they're going to meet and they're going to make a, let's say, if you took a glass, a particular bottle or a particular drinking glass, you turn that upside down, the rim of that glass comes in contact with the surface. It more or less creates a pocket that then we can actually pressurize plus. And out here, of course, we have atmosphere. If we pressurize inside this area, inside this pocket, underneath the measurement head, and we have the measurement head setting on top of the sample, all right? One more step we need to do, we need to support that sample, of course, because if I have a particular measurement head, and put it on top here, there's no means of capturing and creating that pocket. So we've got to support this sample with some type of a firm backing, okay? Now we have more or less a table. Put our sample on, turn the measurement head up on. Now we have a pocket underneath this measurement head, in between this annular ring that we've captured. Now, again, we can create a pressure drop between the area underneath the measurement head and atmosphere. So if we set this device on top of our product, we crank up our air source so that now we have some pressure underneath this area that's higher than atmosphere. What's going to happen if we have any type of topography here is the air is going to leak under the metering lands and out to atmosphere. Okay? So we developed some type of a restriction that we can remanufacture over and over again. We designed this particular measurement head so that we can capture air on top of the surface of our product. We can create an air pocket under here. We can pressurize underneath here, and we can evaluate, much like we did up here. If we have a flow meter in place, we have a pressure regulation in place so that we regulate the pressure under here to a constant pressure. We know what atmospheric pressure is. It's something other than what's under here. We know that we're going to get leakage out of here unless we have a perfectly smooth surface. And we're going to be able to evaluate what kind of air flow is escaping out from underneath this measurement head. That was basically the basic design of our, let's say, our first roughness test. Okay? So we create this pressure drop. We measure the air that's flowing out from underneath these measuring lands, or this pocket, I should say, and we can assess, in a relative sense, what kind of surface topography we have with the product that just came off our paper machine. All right? If that surface is rough, obviously we're going to get a high flow escaping air out from underneath these two annular rings. If that surface is relatively smooth, we're going to increase the restriction because we no longer have a lot of air pockets, a lot of, let's say, passageways underneath these meter glands for the air to escape. All right? Now we've created what will look like future instrumentation that we can utilize, a quick and easy way to assess the surface of the product that we want to send to our customers and meet their specifications in a similar fashion where they provide us a product that they realize is going to give them, in some cases, a pretty good image, okay? In some cases, it's going to give them a pretty bad image. If we have those two levels of, let's say, roughness, okay, much like we made our tolerances, set them up with the dowels, now we can establish, again, in a relative way, what range, quickly, what airflow range is going to be acceptable to our customer. We can keep moving with production. We can get production information. We can get the results of our test back to production, so our production can keep going. Now we have a system that works relatively safely. We still might get some, let's say we still might get some complaints for other purposes, but at least we can establish what that surface and quantify that surface so that we know that if we continue the production in the same way we are and we get good results on our air leak test, that we know that our production is under control. All right? The same thing happens when we start to look at the surface characteristics as they relate to printing or paper transport. We have a system, a quick system, again, where we have the means of quickly evaluating what that product, what that surface looks like, quickly introducing our, the results into our production line and getting the loop closed. Now, we have a system that works. We have two, let's say, relatively groups of instruments that are that we can call roughness and smoothness. What I want to do now is just touch a little bit on the history of this particular test. We have, I mentioned early on that these pieces that I've got out here on the tabletop represent just about everything that you might come across in a typical lab that's assessing the roughness or smoothness of a particular product, whether it's in Europe or whether it's here in the States or South America, anywhere internationally. Somebody out there, if they're selling to the print industry or if they're selling to people who are going to utilize a printer or a xerographic machine, they're going to have some specifications. They're going to know what works for their converting process. They're going to be able to provide us that information so that we can then assess with these tools how our production is working. So now let's cover a little bit of the timeline that we can use to establish when did these instruments come along, how did they come along, what designer came first, just to give you an idea of what happened over the years of development. So, as I mentioned, the air leak test became pretty predominant, again, in the manufacturing industry. Pulp and paper people started to look at it for the application of their particular products. So printing has been done for years. I think maybe even hundreds of years, I'm not quite sure. But somewhere around the late 1800s, early 1900s, now we get this like printing industrial revolution going on. So let's say the requirements for the product that they're printing on becomes a little bit more stringent. Still takes a little bit of time before someone comes up with a design, but somewhere around '30s, okay, development started to occur for the first air leak test for this particular industry. That particular test was a Beck test, B-E-K-K. Julius Beck was the designer of that particular product. He was the first one to take a look at trying to utilize what they did and what they used in other manufacturing areas and try to utilize that particular process or that technology in the pulp and paper industry. So he had one idea. He was a European. His particular product didn't really make it as far as marketing and sales into the U.S. So it wasn't until around the mid-30s, late 30s, the next two devices that came around, somewhere around 1939, I'll say, the next two tools that were introduced was the Teledyne Gurley came up with the SPF, and another gentleman from Europe designed another product that has been referred to as the Benston test. All right. So around 1930, we've got SPS, and we also have the Benston. Okay, so those two tools, the Teledyne Gurley did infiltrate. That was an American company, so that did infiltrate our industry, let's say, to a higher level than the Beck test for sure. The Beck test, we might be able to still find that here in the States. We're doing some exporting, importing, exporting, so the requirements for that particular test might exist here in the States. I don't know personally of too many that are being used out there, but certainly the Benston test became a pretty hot commodity, I guess, in the U.S. to a certain degree for the purposes of exporting product that was made here to Europe. Europe was, again, the European was used, sorry, Tom. The Beck test, of course, was a European design, so that certainly had a bigger influence in Europe and Asia than certainly here in the U.S. There are some companies today still using the Benston test in a variety of different ways, again, for probably more so for the purpose of exporting to outside the USA. Then somewhere around 1950, another gentleman comes along, or another group of people that come along. All right, we'll say I'm going to say somewhere around 1950 to the mid-1950s. Interestingly enough, the Sheffield test was developed, okay? Now we have the Sheffield test. Okay, now interestingly enough, that particular product came out of the automotive industry, where Bendix Sheffield was big into automotive products. Okay, Bendix brakes, of course, was a big one. But they utilized that technology big time in manufacturing. They were the ones who saw it as, I think, as a viable product that they could manufacture and infiltrate the marketplace, of course, and increase some of their market share. So somewhere around 1950s, the Bendix Sheffield Corporation came along with this device. Now, it wasn't until close to the 1950s, so we're looking at probably another 10, 15 years, before another European gentleman, a British gentleman, developed a tool called the Print Surf. Again, another Air Leak tool that could be utilized in the production process to provide a fairly quick assessment of what the surface of that product looked like, bring that to the production people, and either maintain that production level or improve it or change it if necessary. So we've got these 5 devices that have evolved over a time period of somewhere around 30, 35 years. These tools are still relatively popular in assessing the surface characteristics of paper, of polyfilms, and the like still today. Beyond 1963, as far as an air leak tool, there's really been nothing developed. They did do some modifications to the Print Surf test somewhere in the early 90s, maybe late 80s, early 90s. But beyond that period of time, these tools are really have outlasted, let's say, a whole boatload of products out in the area that never lasted to to 50 years, 50 or 60 years like these have. So that gives you a quick and dirty rundown on the development of these tools, a timeline somewhere in the 30s up to the current day. These products are being used. When we get back to the next group of the next series of video tutorials, I'm going to go ahead and I'm going to dive a little bit deeper into the specifics of each one of these tests that I just mentioned here: the Beck test, the Benson test, the SPS test, the Sheffield test, and the Print Surf test. So I appreciate the time that you took listening to me today. Hopefully you'll return, and I'll see you again. Thank you. Bye-bye.